My name is Mark Madison, and I'm here with Terry Wong. We are both chemistry majors at Cal Poly San Luis Obispo. We are doing practice problem chapter 2.4, number 1. This problem deals with Coulomb's law, which Coulomb's law governs the force of attraction between an anion and a cation in an ionic bond, and it is represented by the equation seen right here, where F is the force of attraction between the two. Q plus and Q minus are the charge of the cation and the charge of the anion, respectively. R is the distance between the two nuclei, which can vary depending on how they are oriented. The term 1 over 4 pi ERE naught, we're going to call that Coulomb's constant and represent it with a K from here on out. But the 1 over 4 pi assumes we have a spherical particle. The area of a sphere is 4 pi r squared, which is factored in this equation. ER is the dielectric constant for water, and E naught is the permittivity of free space, which is the capability of a vacuum to permit an electric field. Okay, so let's apply this to a certain situation. We want to find out if a sodium ion is going to be more strongly attracted to a fluoride ion or an oxide ion. So there's a few pieces of information that we need, where we need R, which is the distance between the two atoms, which in this case is going to just be the sum of the two radii, because we are going to assume that they are like so, R. The other things that we need is we need the radii of each of the atoms involved, which are all right here. We have K, we have a value for Coulomb's constant, in this case is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Now Q is the charge of each of our individual species, which the charge of each of these individual species is the number of electrons times the charge on a normal electron, which is this number right here, 1.6 times 10 to the negative 19th coulombs. So let's plug everything in and see which one is going to have the stronger attractive force. So for sodium and oxygen, it's a little bit thick. For sodium and oxygen, the force is going to end up being 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times 1.6 times 10 to the negative 19th. This is for our sodium ion, so it's really plus 1 times E. I'm just leaving that out. Over here, we have negative 2, again, times 1.6 times 10 to the negative 19th coulombs, and this is coulombs over here too. And that is because our oxygen is O2 minus. That is going to be divided by the sum of the two radii, which for sodium is 0.102 times 10 to the negative 9th meters, plus 0.140 times 10 to the negative 9th meters. And we have to square that. So the reason we have it all like this is because we want our units to cancel. We want force to be in newtons, right? So if we look, our coulombs are going to cancel. 1 coulomb, 2 coulomb, square coulomb. Our square meters are also going to cancel because as this is squared, our answer to this term is going to have units of square meters. So we can cancel that with here, which leaves us just with newtons, which is what we wanted. So if you do all of this math out, you're going to get a number which is equal to negative 7.868 times 10 to the negative 9th newtons. Now we expect numbers on this about scale, I'm going to let you know, of about 10 to the negative 6 to negative 9th. That's usually about what we get. Now the significance of this negative sign means that this is an attractive force, which we experience between a positive species and a negative species. Now, let's see what we get for a fluoride ion. we're going to see Na plus and F minus. And our F is going to be equal to 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Times this case, we have +1 and -1 as our charges. We are going to go with 1.6 times 10 to the -19 coulombs times -1 times 1.6 times 10 to the -19th coulombs. And this one is going to be divided by the sum of their ionic radius, again assuming that they are side by side, like so. And so therefore, it is going to be the sum of their individual atomic radii. Plus 0.133 times 10 to the -9th meters for fluorine. And again, that's squared just so all of our units, except for newtons, cancel out. So if you were to do the math here, plug it all into a calculator, you would get a number of -4.172 times 10 to the -9th newtons. So let's look at these two. We're looking at the two forces here and here. So the magnitude of this number is greater than the magnitude of this number, which means that the force of attraction between Na plus and O2 minus is greater than the force of attraction between Na plus and F minus. So now let's see if we would expect a chloride ion to be more attracted to a sodium ion or a potassium ion. So if this term up here remains the same, which it will because all these species have the same charge magnitude of +1 or -1. So now we're only concerned with this part of the term, which is the distance between the two of them. So we know that the force of attraction falls off with distance proportional to the square of the distance between the two of them. So if this potassium ion has a larger radius than the sodium ion, the attractive force is going to be stronger between the sodium and the chloride because those two nuclei are closer together, making this R term smaller than for the potassium and the chloride. Therefore, a chloride ion is going to be more strongly attracted to a sodium ion. So now we're going to imagine that we were able to measure the force of attraction between a sodium and a chloride ion at several different distances between them. So how would we plot this data so that it could be fit with a linear equation? So here's our Coulomb's law right here. Now we chose some arbitrary values for the distance between them just to kind of get some data down. All these Q pluses and Q minuses are going to stay the same, the charges. So what we expect is an exponential decay proportional to 1 over R squared, which is perfect. That's exactly what we get here, is we get a linear decay that is going with the square of the distance. It's exactly what we expect. So now, a neat trick if we want to linearize data such like this, one thing we can do is we can take the natural log of the y-axis to get us a linear function, which is what we did here. We took the natural log of all of our f's. And since all of our f's were less than 1, all of our natural log terms are going to end up being negative, which is why we have a negative slope right here. So, how would your fit line be related to Coulomb's law? Well, if we're able to linearize this data, we know that the slope right here has to be a constant because it's linear. So the only things that are not changing in this whole experiment is the Coulomb's constant, because it's a constant, it's not going anywhere. And then our Q terms. These are the only things that remain constant in this equation because the actual variable that we are changing is the distance between the two atoms.